gone over the first part of this. All right. Let me fill in some of the keywords just in case you missed it. Well, actually no. I'll make sure we talk about this today during class. So then the power rule is where we're going to go next. I know we probably already even talked about it in class a little bit, but in your notes that's where we're going to start. The power rule is like the easy way to do it so you don't have to do the limit process every time. And there's many of these rules that happen. So this pattern brings us the power rule, a very important rule that we use to find the algebraic derivative instead of the numerical derivative. Algebraic is exact, numerical is an estimate. This rule states that if f of x equals x to a power, like x to an n, then f prime, or the derivative, or the speed of that at any given x, is this expression. Okay? Basically, saying that you multiply by the original exponent n, then you reduce the exponent by 1 to get the new exponent. Okay. Yeah, so it might make more sense after we go through an example, and I think we have an example. Yeah, example 2. All right, go ahead and flip. Oh, before that though, sorry. This property works for powers with what we call constant exponents, not variable exponents. That means that this is a number. It can be a fraction, it can be a decimal, but it has to be a number. You cannot have x as an exponent. We'll learn how to deal with those later. They can even be negative numbers. It just has to be a number as an exponent, not a variable. Alright, so the process of finding an equation for the derivative of a function is called differentiation. The word reflects the fact that change in y over change in x is a difference quotient. The corresponding verb is differentiate. Okay, so if you hear differentiation or differentiate, it's asking you to find the derivative. To differentiate a linear combinations just means you're adding and subtracting a bunch of terms of power functions. You must be able to differentiate the sum of two functions, the difference of two functions, and a constant. Following are the rest of the rules that make it possible for us to differentiate several types of functions algebraically, which is to find the exact instantaneous rate of change, not the estimate any longer. Okay? So the first one, sum and difference rule. If f of x equals g of x plus or minus h of x, then f prime of x is equal to g prime of x plus or minus h prime of x. Okay, so to find the derivative of a function, which is made up of two different functions being added or subtracted together, it's just the derivative of, the derivative of this one is the same as the derivative of both of them still being added or subtracted. So if this was like x cubed plus x squared, then f prime would be the derivative of x cubed plus the derivative of x squared. Okay. A constant times a function rule. If f of x equals c f of x, so this would be something like 2x squared, then f prime of x is c times f prime. The c doesn't disappear. That number in front is still technically there, even when you take the derivative of the function. Okay. The last one, constant rule. If f of x equals c, then f prime of x is 0. The reason for this being constants do not change. So their rate of change, or their derivative, is 0. Because if this is fx equals 2, if we were to graph that, it would just be a straight line. And so that doesn't fluctuate or change, therefore the rate of change is always 0. Okay, so basically these three, if you're adding and subtracting two functions, the derivative is the derivatives of those two functions still being added or subtracted. If you have a constant in front, the constant stays. You just multiply it by the derivative. And then here, if you just have a number by itself, then the derivative is 0. Alright, let's look at some examples now. Example 2. Alright, the directions for both of these groups of problems will be to differentiate the following problems. We're going to make an A and a B. Okay, for A, we're going to start with f of x equals x squared plus 2x plus 1. Now, let me state here that we're just doing basic problems here so that we practice a lot. Excuse me, with the power rule, some of the application of this stuff will come later. So this is just basic practice. Alright, if I want to find the derivative of this, the algebraic derivative, I can use the power rule here because all of these are what we call power terms, or there's something raised to a power. X is being technically raised to 1, and my exponents are not a variable, so I can use the power rule. Alright, power rule states that you multiply the term by the original exponent. So the original exponent here was 2. And then you subtract 1 from the exponent. So 2 minus 1 gives you 1. Okay, this next one. My exponent here is 1. I'm going to multiply this by my original exponent. So 2 times 1 is just 2 still. And then I'm going to subtract 1 from the exponent. 1 minus 1 is 0. Well, anything raised to 0 power is just 1, so I'm not even going to write anything down there. And then here, the derivative of 1, since that's just a constant, rate of change of a constant is 0, so it's 0. If you needed a little more step between there and there, this is what we did. We talked through it, but algebraically this is what we did. Subtracted 1 from the exponent, multiplied by 1, subtracted 1 from the exponent, and then had 0. And then it's simplified to this. So 2x plus 1 would be the derivative of that quadratic. Alright, let's look at another one. F of x equals negative 5 halves, x to the 4th plus 12x cubed minus 6x squared minus 1. Okay, so same thing. I'm going to do it the long way and then we're going to simplify it. But if you can go from here to here and not have to do this step, that would be good, since this is supposed to be quick eventually. Alright, so f prime. Again, I can use the power rule in each one of these cases because all my exponents are numbers. I'm going to multiply my constant here, negative 5 halves, by my original exponent, and then subtract 1 from my exponent. I'm going to multiply the 12 by my original exponent, and then subtract 1 from my exponent. I'm going to multiply 6 by my original exponent, subtract 1 from my exponent. And then the derivative of a constant is 0. So let's simplify. F prime of x would be, well, that gives me 20 over 2, so negative 10. X cubed, this is 36. squared. This gives me 12x minus 0. And there's my answer there. Okay. Check on time here. Let's make an A, B, and a C here. For A, we have f of x equals negative 2x to the negative 3 plus 4x cubed minus 2x to the 1/2. So f prime. Okay, I'm going to do this one without writing all the little steps, like up here. F prime, multiply by original exponent. So negative 2 times negative 3 is 6. Then we're going to subtract 1 from the exponent. Multiply by original exponent. So 12, subtract 1 from your exponent. Multiply by original exponent, so 1, and subtract 1 from your exponent. And that would be your answer. Okay, next one. Yeah, I guess we'll do this one. 7 times negative 4/5 x to the negative 9/5. Now, sometimes they'll throw stuff like this at you, and I don't know why they pull out the 7, but sometimes they do. So if you see something like this, if there's no exponent outside the parentheses, we can just distribute through. So I might do a little simplification here and make this negative 28 over 5 times x to the negative 9/5. And then that's what I'm going to take the derivative of. Okay, so f prime of x. I multiply by my original exponent. So technically here, I have negative 9/5 times negative 28 over 5. So let's go 28 times 9 gives me 252 over 25. Then I'm going to subtract 1 from the exponent. When you subtract 1 from the exponent, really what you're doing is you're subtracting 5 over 5. So you should get negative 14/5. And that would be your answer. Okay, let's look at one that might be a little tricky here. Okay, now if you have something that looks like this, try to simplify it a little bit. So maybe I distribute the exponent through, so I get 8x cubed. Now, with the power rule will only work if it's written like this, meaning the x is not in the denominator, but the x is in the numerator. So what we can do here is use our rules of exponents and actually bring that x cubed up to the numerator by making it a negative exponent. You can write it like that, or you can write it like this. Okay, because remember with negative exponents, all it means is that you flip it or use the reciprocal. So I'm going to use this and take the derivative of that piece. Multiply by the original exponent, so we get negative 15 over 8. Then we're going to subtract 1 from the exponent. So technically, we could rewrite this as negative 15 over 8x to the 4th, because they're the same thing. But leaving it like this is probably fine and sufficient. Okay. And then I think for example 4 and 5, I'm going to wait on those until this weekend's video, because that will lead in good into the next section here. So that's where we'll stop.